Hey, welcome back for another deep dive. This time, we're going all the way to the end of the actinide series, to Lorenzium,
Lorenzium, element 103.
a synthetic element, which means, of course,
Not found in nature.
not found in nature, and it's radioactive too. And of course, is named after
Ernest Lawrence.
Ernest Lawrence, the inventor of the cyclotron, who, I mean, what a fascinating story. Just to think about how...
It really is. You
Yeah.
know, to synthesize an element like Lorenzium, it's almost like, I always imagine it as like trying to build a tower out of incredibly slippery magnetic blocks.
Oh, wow.
You know, so the heavier the element is, the more these blocks, which are the protons in the nucleus,
Right.
repel each other.
Okay. Yeah, that makes sense. So how do they even create these super heavy elements then?
Well, they use these incredible machines called particle accelerators, which smash lighter elements together at near the speed of light.
Oh, wow.
So you're taking, you know, two atoms and just slamming them together,
Yeah.
hoping that they'll stick.
Wow. So what are the odds of that fusion actually occurring?
The odds are incredibly slim. You know, it's a very delicate dance of energy and timing
I think
to actually get them to fuse.
it sounds almost impossible. And then even if they create it, it doesn't last very long.
Right, exactly. You know, even if you manage to create a new element, it often exists for just a fleeting moment before it decays.
Okay.
And that brings us to a fascinating period in scientific history, what's often referred to as the Transfermium Wars.
Ooh, I love a good name like that. What are the Transfermium Wars?
So this was, this was during the Cold War.
Okay.
And the Cold War rivalry really spilled over into the world of super heavy element research. So you had, the U.S. and the Soviet Union locked in this very intense competition to synthesize and name new elements.
So it wasn't just about scientific discovery. It was also about like national pride.
Right. Oh, absolutely. This was, this was a battle for scientific prestige.
Wow.
And Lorenzium, or element 103, became a focal point in this.
So who are the main players in these Transfermium Wars?
So you had the team at Berkeley Lab in the U.S., and you had the scientists at the Joint Institute for Nuclear Research in Dubna, which is in the Soviet Union.
Okay.
And both teams were confident that they had synthesized Lorenzium first.
Oh, so there were conflicting claims. Like, were they publishing papers? And
Absolutely. It was a very, there were scientific papers fired back and forth,
Wow.
kind of like intellectual missiles almost.
That's amazing. So how did this scientific showdown eventually resolve? Did anyone claim victory?
It took decades, actually. The International Union of Pure and Applied Chemistry.
Oh, the IUP.
Yeah, IUPAC, yeah, the referees of the chemical world, right? They finally stepped in and in a diplomatic move, acknowledged both teams as co-discoverers of element 103 in 1992. So they did retain the name Lorenzium, but they did change the symbol to Eller instead of Berkeley's proposed LW.
Oh, okay.
So
So it was a bit of a kind of a compromise.
yeah, a little bit of a compromise there, but at least it recognized the contribution of
Okay.
both teams. Yeah. Okay, so besides this whole scientific rivalry, what makes Lorenzium so interesting, so special from like a purely chemical standpoint?
Well, Lorenzium is fascinating because it kind of sits at this intersection of two groups of elements. You have the actinides, and then you have the group 3 transition metals. It's almost like it's trying to decide which family it belongs to.
Oh, okay. So tell me more about this kind of this identity crisis that it seems to have.
Well, chemically, Lorenzium behaves very similarly to its counterpart in the lanthanide series, which is lutetium.
Okay.
So they both have a tendency to lose 3 electrons,
Okay.
forming what we call a +3 charge when they react.
Mm-hmm. But their electron arrangements, or what we call their configurations, tell a slightly different story.
Okay, so I'm sensing a curveball coming here. What's going on?
Exactly. So, you can picture electrons as kind of fitting into these specific slots, or what we call orbitals, around an atom.
Okay.
Now, based on its position on the periodic table, you would expect Lorenzium's final electron to land in what's called a day orbital, just like lutetium. But guess what? It prefers a p orbital instead.
So it's breaking the pattern, kind of like a rebellious teenager.
That's a great way to put it. And this kind of defiance of expectations has really puzzled scientists for quite some time.
So what does this mean for Lorenzium's behavior? Does it actually act differently because of this configuration anomaly.
That's the fascinating part. Despite this deviation, Lorenzium's chemistry remains incredibly similar to lutetium.
Oh, wow.
So it kind of raises all these questions about, how these electron configurations actually translate into, real-world chemical behavior.
So I guess even though we have these like neat and tidy models and we think we know how things work,
Yeah.
nature always finds a way to kind of...
Absolutely. It's a reminder that even in a field that seems as kind of well-defined as chemistry,
Right.
there are still so many mysteries
Yeah.
to unravel, deeper layers to understand.
This deep dive is already blowing my mind, and we haven't even gotten to the island of stability yet. That just sounds like something straight out of like, a science fiction novel.
It does have a certain ring to it, doesn't it?
It really does.
But it's a very real concept in nuclear physics.
Okay.
And it's closely tied to our quest to create even heavier elements. So essentially, it's a theoretical region on what's called the chart of nuclides, where super heavy elements, which are normally incredibly unstable,
Right.
might have surprisingly long lifespans.
Oh, okay.
Yeah.
So where does Lorenzium fit into all of this?
Well, most of the Lorenzium isotopes that we've created have very short half-lives. They decay rapidly.
Yep.
But there's one, Lawrencium-266, that has a half-life of about 11 hours.
11 hours.
Yeah.
And that's long.
In the realm of super heavy elements, that's practically an eternity.
Wow. Okay. So even just this like slightly longer lifespan is significant in this context. Like it's a hint that maybe we're on the right track towards this island.
Exactly. It's like while Lorenzium itself might not be on the island,
Right.
its properties kind of offer these valuable clues about the region's existence and what we might find there.
Okay.
You see, the stability of a nucleus is governed by a very complex interplay of forces.
Okay, break that down for me. What forces are we talking about here?
So imagine the nucleus as this bustling city, right?
Yeah.
And the protons are like the residents who all want their own space. And as more and more residents move in, so the city becomes more and more dense, right?
Okay. Right.
The repulsion between them increases.
Okay, so too many residents, too much repulsion,
Yeah.
and things start to kind of...
Things start to fall apart.
Yeah, yeah.
That's what happens with a lot of these super heavy elements. They're just not stable.
Right.
But the island of stability theory suggests that at certain what we call magic numbers of protons and neutrons,
Uh-huh.
this urban sprawl, so to speak, can reach a stable equilibrium. It's like finding the perfect layout that allows everyone to coexist peacefully.
Oh, I see. So it's about finding the right combination of protons and neutrons to achieve this like harmonious nuclear city.
Precisely. And theoretical calculations suggest that this island of stability might exist, around element 114 or 120.
Oh, wow.
Or perhaps even further out.
So if Lorenzium is like, a coastal city that's kind of hinting at the existence of an island out there, how do we actually get to the island? How do scientists use this element as a springboard to reach these heavier elements?
Yeah.
Well, think of Lorenzium as a base camp, right?
Oh,
From which explorers set out to reach these distant shores. So they use it as a target in particle accelerators, bombarding it with beams of carefully selected lighter elements, hoping to fuse them and create even heavier elements.
So it's a really, really delicate and challenging process, but every step forward adds to our understanding
Exactly.
of this crazy world.
Yeah.
Yeah. I think we need to take a short break.
Okay.
We'll be right back with more of this deep dive into Lorenzium.
So we've talked about how Lorenzium can act as this launch pad, right,
Yeah.
to reach even heavier element. It's it's pointing us towards this elusive island of stability.
It really is. It's fascinating how this element that, as we've established, isn't even found in nature, it's man-made, can actually guide us towards
Right.
these new discoveries, potential discoveries. So if we kind of zoom out a little bit, what is the bigger picture here? Why are scientists so eager to reach this island of stability? What's the big payoff?
Well, the potential discoveries and applications associated with these super heavy elements are truly mind-boggling.
Okay.
Just to imagine elements with properties that we've never encountered before.
Yeah.
Materials with unprecedented strength or conductivity.
Right.
It could revolutionize fields like material science and energy production.
It does sound pretty incredible.
Yeah.
But if these elements are so potentially valuable, why haven't we found them in nature?
Well, that's the thing, right? The very forces that make them so fascinating are the same ones that make them incredibly unstable in our everyday world.
Okay.
Remember that bustling city analogy we were talking about earlier?
Yeah.
In most super-heavy elements, the repulsion between the protons and the nucleus is so strong that the nucleus just quickly falls apart.
Oh.
It decays before it has a chance to form any lasting structures.
So the island of stability represents kind of this haven, this safe space for these elements where those repulsive forces are balanced.
Right.
And they're allowed to exist for much longer.
Exactly. It's like finding this rare oasis in a vast desert, right?
All right.
And the discovery of even slightly more stable isotopes like Lorenzium 266 with its 11-hour half-life provides us this tantalizing glimpse of what might be possible.
So Lorenzium isn't just like this stepping stone to heavier elements. It's also like a window into these principles of nuclear stability itself.
Exactly.
Like it's helping us understand this very delicate balance
of
forces that actually govern the existence of matter.
It really is, and that knowledge has far-reaching implications.
Right.
It helps us understand the processes that are occurring in streams, the origins of the elements in the universe, and it could even lead to technological innovations here on Earth.
I never thought I'd see the day when a synthetic element could shed light on the mysteries of the cosmos.
It really is. It's a testament to the interconnectedness of science, I think, and the fact that even seemingly obscure discoveries can have these profound implications.
So back to this quest to reach the island of stability.
Yeah.
How are scientists actually using Lorenzium to inch their way towards this nuclear haven?
Well, imagine you're an archer.
Okay.
And you're trying to hit this tiny target in the distance.
Uh-huh.
Lorenzium and other heavy elements like it act as the arrows, right, in this scenario.
Okay.
And they are fired from a particle accelerator towards a target that's made of another heavy element.
Okay.
And the goal is to score this direct hit, causing the nuclei to fuse and create a new, even heavier element.
So it's like a microscopic game of billiards played at incredibly high speeds.
That's a great analogy. Yeah, and it requires this incredible level of precision and control, right? The beams of these arrows have to be meticulously focused, and the collisions have to be perfectly timed.
I can't even imagine the complexity involved in something like that.
Oh, it's extremely complex.
So what are some of the biggest challenges that scientists face in this quest?
Well, the main hurdle, as we've kind of already touched upon, is the inherent instability of these super heavy elements. The nuclei are like fragile glass ornaments. They can shatter at the slightest touch.
Right.
So not only is it difficult to create them, it's also incredibly challenging to actually study them before they decay.
So it's this race against time, this delicate dance of precision and fleeting existence. So what kind of information are scientists trying to glean from these fleeting moments?
Well, they measure everything they can.
Okay.
The decay modes, the half-lives, the energies involved, all of these data points help us to understand the forces at play and refine our models of nuclear structure.
So it's like trying to piece together a puzzle with disappearing pieces.
It really is.
But I guess even those fleeting glimpses can provide some really valuable clues.
Absolutely. Each successful synthesis, even if it only lasts for, a fraction of a second, adds to our understanding of this landscape of the island of stability and helps us to kind of, navigate towards its shores.
This is also fascinating.
Yeah.
But before we get lost in the sea of super heavy elements here,
sure,
I think we need to take another short break. We'll be back soon with the final part of our deep dive into Lorenzium. Welcome back to our deep dive into the fascinating world of Lorenzium. We've covered a lot of ground, from the Transfermium Wars to this idea of the island of stability.
Yeah.
It's incredible how an element that's only synthesized in a lab could hold so many secrets and breakthroughs,
Yeah,
potentially.
there he is.
Yeah, it makes you wonder about all the other connections in the universe we just haven't found yet.
Right.
So as we set sail, so to speak, for this final leg of our Lorenzium journey, what what are some of the uncharted territories still left to explore in this area of research? What are we still looking for?
Well, one of the biggest questions that still lingers is the exact location and nature of the island of stability, right?
Right.
We have these theoretical models, but pinning down its exact coordinates, on the chart of nuclides, it's still a major challenge.
So it's like we have a compass, but we're still navigating through a dense fog.
That's a great analogy. Yeah, we're relying on this combination of theoretical calculations and experimental observations, and each new element we synthesize, each data point we collect, kind of helps to refine that understanding.
It sounds like trying to build a sandcastle on a windy beach.
Right.
But the sandcastles are atomic nuclei,
Right.
and
Exactly.
the wind is their instability.
Yeah, it's certainly not for the faint of heart.
No.
But the rewards are potentially immense, right? I mean, imagine if we could unlock the secrets of these stable, super heavy elements. New materials with unheard of properties, revolutionize energy production. Even open up new avenues in medicine and technology.
It's almost overwhelming to think about the potential impact of all of this, but we're still kind of in those early stages of exploration.
Yeah, we're pushing those boundaries one atom at a time.
One atom at a time. Wow. What are some of the specific research efforts that are underway right now?
Well, a lot of it focuses on developing these new experimental techniques, right? Think of it as upgrading our tools
Okay.
for this atomic level exploration.
I like that.
Yeah, scientists are constantly working to improve, particle accelerators,
Right.
creating more intense beams and refining their control over these high energy collisions.
So we're building bigger and better telescopes,
Hmm.
but instead of peering into the cosmos,
Hmm.
we're looking at atoms.
Precisely. Yeah, and these advancements aren't just about, creating new elements. It's
Right.
also about characterizing their properties in more detail, right?
Right.
So we're developing these new detectors and measurement techniques that can capture those fleeting moments of existence
Yeah.
and provide us with this richer understanding of their nuclear and chemical behavior.
So it's a two-pronged approach then.
Yeah.
We're creating them, and then we're quickly trying to analyze them.
Absolutely. And it's not just about the tools and technique.
Right.
It's about the collaboration, the ingenuity of scientists around the world.
Yeah.
This is a truly global effort
Yeah.
with researchers sharing data, sharing insights, sharing expertise, and it's all to kind of push the boundaries of human knowledge.
It's heartening to hear about that kind of collaboration in a world that often feels very, very divided.
It really is, and who knows, maybe someday, thanks to those collaborative efforts, we will finally reach the shores of the island of stability.
That would be incredible.
It would be incredible, right? It would unlock this whole new era of scientific discovery and technological advancement.
Well, what a journey this has been. From electron configurations to the Cold War and this idea of a mystical island of stability.
It's amazing to think that Lorenzium can teach us so much
It really is.
about the universe, about matter, about everything.
So to our listener, we'll leave you with this final thought. The exploration of the periodic table is far from over, and Lorenzium has shown us that even the most synthetic man-made elements can hold the keys to some of the universe's biggest secrets. Thanks for joining us on this deep dive of the deep dive.